Okay, so who remembers what we were talking about a week ago? Okay, so yeah, and that's right. And generally, we were talking about the force types, right? Don't look in your notes. It's cheating. That you get the penalty bell. So what are the force types that we've dealt with?
Push and pull, right?
That's right. Well, I'll do them in order. So there was one before that. It was such a quick and easy one that we didn't talk about it much. Weight, yeah. I just did 2 number ones. This means bless you. Pushing contact, pulling contact, friction, and there's one more to go. That's right. So that's the one that we're doing today. Okay, so if you have, so this is the one for today. And then after we're done with that, I don't know how much we'll get to this, how much of this we'll get to today, but we're going to go to Newton's third law. And then I'm going to give a little bit more detail on what's required in free body diagrams. So far, I've just been drawing them. You've been drawing them, but I'm going to give some rules now that you've gotten all your bad habits. Wait, that's not a good idea. Free body diagram rules. Okay, so let's say that we have this object connected like to the wall by a spring. And we're going to talk about the force that the spring applies to the chosen object. And before we can do that, we have to define 1, 2, 3, 4 things. The first one is every spring has a resting length. You know, like if you have a drawer with springs in it, they're all a certain length when they're sitting there. And so I'm going to call that L sub 0. So that's the length of the spring when no force is applied to either end of it. The second one is what happens when you apply force to the ends of a spring. Yep. And, well, it could stretch or it could compress, but the length is going to change. So we also need like a current length, a deformed length of the spring. And the difference between those two is going to be important. And so the third one is delta L, the change in L. And that's just L minus L sub 0. So with this one, notice if the spring lengthens, what's the sign of delta L? Okay. It works. You do get smarter. And if the spring shortens, what's the sign? Yep. And then the last definition is one that this is just a definition of an individual spring. Do you have a question? Oh. So a spring, you know, some springs are super stiff, like struts in a car, shocks in a car. Those are really stiff springs, you know. Like it would take a lot of force to change the length. Some little skinny springs, it doesn't take much force at all to stretch them out a foot. So we need something to define that. And that's going to be the constant K. We'll call that the spring constant or the spring stiffness. It has units of force per length. And that means that the SI units are newtons per meter. This spring constant is always positive. A large value means that the spring is really stiff. It's hard to deform. And a small value means that it's easy to deform. Okay, so given these four definitions, the force applied to an object by the spring is equal to the spring constant times delta L, which you can also write as K times the quantity L minus L sub 0. That's the magnitude, or that's the constant that you're multiplying by the direction that's going in a certain direction. And the direction is away from the chosen object toward the spring. So the direction is going to be like a cable tension. Okay, we're going to draw the direction like a cable tension. There's a difference, though, with tension, and that is that K times the quantity L minus L sub 0 can be positive or negative. Cable tension can't ever be negative. So if this quantity L minus L0 is negative, that switches the direction. And that's because a vector in this direction with a value of 5, or I guess this direction with a value of negative 5, let's say, is the same thing as a vector in this direction with a value of positive 5. Okay. Everyone with me on that? Okay. All right, so let's do some examples. So let's say we have a 2-kilogram cart with a 10 Newton force applied to the left. What? Just, no, let's have it going in that direction. Yep. So that could be applied by a cable or something. And let's say that this spring has a spring constant of 150 newtons per meter. If the spring's resting length is 8 centimeters, so 0.08 meters, bless you. What's the length in the system as it's shown? Okay. So how are we going to do this? How indeed. Okay, so we're going to use Newton's second law, so we're going to start with a free body diagram. What forces are acting? What? Yeah, let's go in order, though. I like the repetition. So first one is weight. So 2 times 9.81, that's 19.62 down. Then we'll go around looking for contact, so the 10 Newton force, like you said. Then what's going on at the wheels? There's contact with the floor. So what does that contact force look like? In problems where, yeah, it's a pushing contact, right? So a normal force. The wheels mean that we're ignoring friction, unless it says that there's some kind of wheel friction. Well, I don't think we're dealing with that in this class anyways. And now there's the force applied by the spring. So the way we're going to represent that is we're going to assume that it's going this direction. The value is going to be 150 times the length minus the resting length. and it's just possible that that length is going to come out to be like if that length comes out to be less than 0.08, it means that this force would be going the other direction. But we're just always going to assume that it's pulling and just calculate if it goes the other way. Okay. Any questions about that free body diagram? Okay, so now Newton's second law. That 10 Newton force, what's that in vector components?
Negative 10, 0.
Yep. Negative 10, 0. How about the weight? Yep. How about the normal force? Yep. And then this one, how are we going to represent this? Well, you can think of it as, I think the best way to think about it is it has a magnitude of 150 times the quantity L minus 0.08, and it's in the direction of positive x, so it's that times that direction. You see what I mean? And we're assuming that that this comes out to an equilibrium position. So if it's an equilibrium, then there's no acceleration. And so we get two equations here. The first one says negative 10 plus 150 times the quantity L minus 0.08 is equal to 0. The second one we could use to calculate n, but the question doesn't ask about that. And so 10 is equal to 150 L minus 0.08. So L is equal to 0.1467. Any questions about that? Yep. Oh, because, so why can you? I suppose really, I probably should have said that clearly in the problem. But as long as that 10 Newton force, so the thing with springs is, it's an approximation, but you assume that the length of the spring is only related to the forces applied. Okay? If you apply a certain force to it, you get an instantaneous change in length. And so as long as the force is a set thing, the length is a set thing, and so you can't have any velocity or acceleration. Does that make sense? Okay. So we'll just keep ramping these up a little bit. Oh, actually, before we do this next one, let me give you one to think about. So let's say that you got your dream job in a spring factory. Finally, all your hard work paid off. And so your boss is like, get me that spring constant for this spring. I need it by Tuesday. It's important work, though. Okay, so let's say that what you do is you take this spring with a resting length of 0.05 meters, and you hang a mass of 0.5 kilograms from it. And when you do that, the hanging length is 0.09 meters. What's the spring constant? Okay, and don't do this in your head. I want you to go up to the board, draw a free body diagram, write out Newton's second law. So yeah, everybody did that great. So the free body diagram. You have the weight down of 4.905. You have the force up, that's the spring constant that we're trying to find, times the current length minus the resting length. And it's at rest, so there's no acceleration. So Newton's second law says 0, negative 4.905. Plus 0, k times 0.04 is equal to zeros. And so the second equation there says 0.04k is equal to 4.905. And so k is equal to, what was it, 122 newtons per meter. Okay. Okay, so now let's do a little harder one. So now let's say that there are two carts. Don't make me ring the bell again. Unless you sneeze, you can't help that. Okay, so 20 newtons there. The spring constant is 400 newtons per meter. What's the change in the length of the spring? Okay, so how are we going to do this? Well, really the approach is the same as if these were just touching each other. We're going to isolate the whole thing, calculate the acceleration, and then we're going to isolate a single one to calculate that spring force, or to use the spring force to calculate that change in length. So a free body diagram of the whole system. Well, we have the weight of 7 times 9.81, so 68.86. We have a force coming up on the wheels. I'll call that N total. We have the 20 Newton force here. Anything else? How do you know when you're done? So we applied the weight, right? The weight's in there. And then we went around the boundary looking for contact with the outside world. There's no more, so we're done. Okay? So Newton's second law. And what about the spring force? Why isn't that in there? What? It's an internal force, that's right. So it'll come up when we isolate one of these two carts, but it doesn't come up when we isolate both of them. So Newton's second law says 20, 0 plus, what's the force vector for the normal force? Yep. And for the weight? Okay, and that's equal to the mass of the whole system times, what do we know about the acceleration? It's horizontal, yep. So just like we did with when these are being pushed. Charlie, that's, you can think of that as like an alarm clock. Okay. So the first equation says 20 is equal to 7a. So a is equal to 20 divided by 7 is, I have it here, 2.857. This is the acceleration vector. So this tells us that the acceleration vector, plug this value in here, and you get 2.8570. Okay, so now let's isolate the 5 kilogram cart. What forces are acting on the 5 kilogram cart? Someone do the easy one. You can do that without even knowing what this problem is. What? You have to know what the problem is for that one. Wait. Okay, and then there's the 20. And then there's a pushing contact. I'll call that N5 from the floor. And then what else? There's one I'm missing. Yep. And so we're going to do that as a tension force with a magnitude of 400 times, we're trying to calculate delta L, right? So I can just write this as 400 times delta L. Anything else? Do we need anything else for this? Okay, that's right. So Newton's second law says 20, 0 plus 0, negative 49.05 plus 0, N5 plus, this is in the positive x direction, so 400 delta L 0 is equal to the mass times the acceleration vector. And so the first equation says 20 plus 400 delta L is equal to 5 times 2.857. That is, I don't know. 14.285. And so 400 delta L is equal to negative 5.715. So delta L is equal to negative 0.0143. So what does that say about the change in the spring length? What? It's less than. Yeah, that's right. It's compressing. Exactly. Okay, so now what I want you to do is go back to the board and do the second part of this problem, but instead of isolating the 5 kilogram block, isolate the 2 kilogram block. Okay? So you can assume you already know that acceleration, but isolate the 2 kilogram. Anybody have a guess what the answer should be? The same, yeah. Better be the same, or we have a problem. Okay. So, yeah, that looks great. So, free body diagram of the 2 kilogram block. So we have the weight of 19.62, the contact force with the ground, the normal force, I'll call that N2. And then we have the force going to the left of 400 delta L. So Newton's second law says negative 400 delta L 0 plus 0, negative 19.62 plus 0 N2 is equal to the mass times the acceleration. Is that 857? Yeah. And so you get negative 400 delta L is equal to positive 5. What do you get there? What's 2 times this? 5.714. Okay. And then
that last number is a 4, I think.
Yeah, right. So that's a round off difference that we have for the 2 parts. And so delta L comes out to be slightly different just because of round off, but I think you can believe that the answer should be the same. So what do you get for that? Basically the same thing, 1, 4, 3. We're off in that decimal place. Yes, thank you. So that means compression. Okay, here's another one for you to work on. So you have a 1 kilogram cart attached over a pulley to a 0.2 kilogram cart. This spring constant is 250 newtons per meter, and this system is at rest. It's
Until it crashes.
long enough. How much is the spring stretched? Okay, do it. Do one more example here. So this one. No, why don't you do this one? You'll like it. Okay, so now let's say that we have a cart swinging around a circular path. And it's connected to the center of the circle by a spring. And the mass is 100 grams. The spring constant is 200 newtons per meter. The spring's resting length is 0.10 meters, 10 centimeters. And let's say the cart's in uniform circular motion. So it moves around the circle with a constant angular velocity of 5 radians per second. What's the length of the spring? Okay, so before you start doing this calculation, can you intuitively tell what's going to happen? I mean, what's going to happen to the length of the spring compared to its resting length? It's going to be longer, yeah, like that that centripetal force that's required to move it in a circle is going to cause that, is supplied by the spring, and that means that it's going to stretch. Okay, so see if you can make some sense out of that one.
Yes, my goal in life has been achieved.
Okay, so I'm going to do a view from the side. So there's a weight. What was the weight? 0.1. So this is 0.981 down. Then we have a normal force, N. And then the only other place there's contact is the force of the spring. And that's equal to the spring constant times the current length minus the resting length. And this is circular motion, so we know something about the acceleration. So before we do Newton's second law, we have to figure that out. So the total acceleration is equal to, in this case, just the centripetal acceleration, because the angular velocity is constant. So usually you break it up into those two, but this one's 0 in this case. And so the centripetal acceleration is the angular velocity squared times the radius, and we know it's pointed this direction, toward the center of the circle. Does all that reasoning make sense? Okay, and then we have to think about what that radius is, and it turns out that radius is just going to be equal to the current length. So the total acceleration is equal to negative omega squared L 0, and omega is 5, so that's negative 25 L 0. And so now we can put it all into Newton's second law. We have 0, negative 0.981, plus 0, n, plus negative 200, L minus 0.1, 0, is equal to the mass times the acceleration. And so the first equation says negative 200 times L minus 0.1 is equal to negative 2.5 L. You can cancel the negatives. So you get 197.5 L is equal to 20. And I actually got something different than you did, I think. Doesn't that come out to be L equal to 0.1013? Can someone divide that out?
We forgot to multiply 0.1 by the...
Oh, okay. Okay. So yeah, the algebra got you.
But 197.5 doesn't equal 0.10. Oh,
It doesn't?
Yes, it does.
Okay.
Never mind.
Okay, so this is something, we're not going to do any calculations with this yet, but I want you to think about, so what would happen, so imagine a cart. So imagine you have this little frictionless rolling thing attached to a spring that's attached to the wall. And you pull it out away from the wall an inch or something, and then let it go. What's going to happen to the system? It'll go back, and then what will it do? When will it stop? Can you picture what would happen? It would actually oscillate back and forth. And does that make sense intuitively? And the speed of that oscillation depends on two things. Can you think of what those two things would be?
The mass of the object.
The mass, and one other thing, and the spring constant. If the spring constant is bigger, so if the spring constant is bigger, the thing will vibrate faster. Okay? And if the mass is bigger, the thing will vibrate slower because it'll take more force to turn it around. And so let me show you how that works. So let's say that this has a mass of m. This has a spring constant of k. And we'll say at time equals 0. Okay, so let me set a couple things up before I do that. So put the origin at the object's location when the spring is at its resting length. Then notice that x is equal to delta L. Wherever it stretches or compresses, the x position gives you the delta L. At time equals 0, let's say you pull the x back to, I don't know, positive point, well, let's just say to positive a. And release it. And let's calculate what happens over time. Okay? So we want to calculate the x position as a function of time. So free body diagram looks like this. We have the weight down, that's mg. We have a normal force up. And we have a spring force that's equal to k times x. Okay? Newton's second law then says negative kx 0 plus 0 negative mg plus 0n is equal to the mass times the acceleration. What do we know about the acceleration? Not much, but we do know one thing about it. It's horizontal. So we'll write this as ma0. And now here's the thing that we haven't done. We did a little bit of this kind of thinking at the beginning of the class, but we haven't done it much recently. But that acceleration is the second derivative of the position with respect to time. So that first equation says negative kx is equal to ma, and you can rewrite that as negative kx is equal to m times the second derivative of x with respect to time. So in other words, negative k over m times x is equal to the second derivative with respect to time. Can you think of any functions that would satisfy that? There are two possibilities. Sine and cosine, yeah, very good. And so in this case, it's going to be cosine. And so the answer is x of t is equal to a times the cosine of square root of k over m times t. You don't have to know how to do that, but it's really just taking integrals and then matching up the constants of integration. And this term here gives you the frequency of the oscillations. So if you increase k, you get faster oscillations. And you can think about just graphing out this function. You know that increasing the constant that you're multiplying by t is going to make those oscillations happen more quickly in time. Making k smaller, making m bigger will slow down the oscillations in time. Okay. So we'll talk about that in an easier way when we talk about conservation of energy, but this is a way you can do it too with differential equations. Any questions about that? You don't have to make sense out of that yet, but it's kind of a first look at oscillations with springs. And I'll bet sometime during Calc 1 you did an example that was like that, but it's hard to remember just random examples thrown out there, but I'll bet you've actually seen that problem before. Okay, so now we're to the second most important principle in this class. The first one is Newton's second law. This one is Newton's third law. And I'm going to abbreviate it N3L. And this is the one that says, the way that it's worded in the original manuscript is, for every action there's an equal and opposite reaction. That's a terrible way to remember it, though. It's very hard to make sense out of that, so I'll try to give it to you in a way that's easier to sort of digest and use. But you've heard that phrase before, right? So the way to really think about it is, for any force occurring between bodies A and B, the force vector on A by B is equal and opposite to the force vector on B by A. That's kind of you can think of that as like the working definition of Newton's third law. Okay, so as far as understanding this, making sense out of it, there are some ways that it makes sense to us and some ways that it doesn't, that it kind of goes against our intuition. It makes sense, I think, if you think about, like, okay, it's visualization time. Charlie's one step ahead of you. He's already in full relaxation mode. Okay, so now picture yourself, you're outside, it's a beautiful day, you're barefoot on the grass, okay? And you're minding your own business and a soccer ball rolls up to your feet, okay? Can you picture it? Are you picturing it? Okay. And you look up and there's a kid 20 feet away, not very far away. And the kid asks you to kick it back, right? Remember, you're barefoot. You can feel the grass in your toes, okay? So it's 20 feet away. You just nudge the ball back over. No problem, right? So now imagine that the same thing happens. You're still barefoot. You can feel the grass on your feet. But the ball rolls up to you, and you look up, and the kid's like 50 yards away, and he yells, "Hey, kick the ball back over here," to you. So what thought occurs to you? Snow it, throw it. You put your shoe on. Okay, so that's what I'm getting at. Is you're a little more reluctant to do it because you know that to kick the ball 50 yards, you're going to have to put a lot of force into that ball. And because of Newton's third law, that ball is going to put a lot of force into your foot.
It could break your toe.
Or at least it'll sting or whatever, you know. And so in that sense, if you think about that example, it makes perfect sense. Newton's third law makes perfect sense, right? Right? Are you with me? You see how that relates to Newton's third law? Okay. So here's one where it's a little more confusing. And I'll try to like explain how it actually doesn't go against Newton's third law. When you see like a home run hitter in Major League Baseball, you know, the ball comes in, the player hits it, the ball flies 400 feet, the player flies 0 feet. So in a sense, it seems sort of counterintuitive, like that ball applied the same amount of force to the bat that the bat applied to the ball. That seems a little odd, doesn't it? I mean, I think that can sort of mess with your intuition a little bit. But there are other reasons besides that force. Like, in fact, the ball does apply the same magnitude of force to the bat that the bat does to the ball. It's just that bat has a lot of unfair advantages in this fight to, like, if they're both trying to knock each other 400 feet, it's not a very fair fight. The bat, first of all, has a lot more mass than the ball does. So the same amount of force is going to accelerate it less. Also, the bat is being held by a 220-pound person. So that makes the bat even less likely to accelerate. And then third, that 220-pound person has cleats dug into the ground, and the earth has a lot of mass. And and so in the end, you never see it'd be cool if every once in a while, you know, the ball stayed there and the guy went flying 400 feet, but that never happens. But it's not because the forces are different. It's just because of all these other things going on that's giving the bat this big advantage. Okay, so every time I've taught physics since I started teaching here, I've drawn this example, and I'm going to do it this time too in honor of my high school physics teacher. So when I took physics for the first time in high school, there was this hot young boxing prodigy coming up. He hadn't won any titles yet, but he was like, everyone was talking about him because he was just like going through heavyweight division like a buzzsaw, and everybody's like, he's going to get a title shot soon. So yeah, that's how old I am. This was Mike Tyson. He was like 18 or something at the time, and everyone Mike Tyson fought just was knocked out brutally in round one. He was just like, everyone was talking about him. And my physics teacher was this 50-year-old, like super out of shape guy. And he's like, you know what? I wish I could have a chance to fight Mike Tyson. I guarantee you, if they gave me the title shot, I could hit Mike Tyson as hard as he hits me. And he drew this picture, which was really freaking funny. Okay, so this is Mike Tyson's glove. This is my physics teacher's face. And it's funny because if you really technically, like if you draw the free body diagrams, there's the arm. There's a force R applied to the glove. That's exactly equal and opposite to the force applied to the face by the glove. Like it's a totally factually true statement. And boxers do occasionally, like actually pretty often in fights, they'll break their hands, because their hands are absorbing. But it's funny because it's not a very good strategy to win a boxing match to attack someone's glove with your face, It's not a it's not a good strategy, but it's totally true. Okay, and so mathematically, the way you're going to use this is to use Newton's third law. When you're going from the force on somebody A by somebody B to the force on B by A, the way to do it is keep the label of the force the same. So that's the R that I did above, that I showed above. Okay, the label of that force is R, and it's the same here as it is here, but the direction is opposite. So draw the arrow the opposite direction. Okay, so I'll start on Thursday with some examples of using this. And, okay, that's all. Any questions about that? Okay, this is the class dismissed bell.